On the 2nd of July, 2025, a satellite orbiting Earth caught something that shouldn't have been possible. A burst of energy from deep space, so violent and so long-lasting that when astronomers finally worked out what they were looking at, several of them independently reached for the same word: incompatible. Not unusual, not rare. Incompatible with every model we have for how something like this is supposed to die. This is the story of GRB 250702b, the longest, most energetic cosmic explosion ever recorded, and the object at the center of it that James Webb Space Telescope has spent the better part of a year trying to identify, without fully succeeding. Picture it the way astronomers eventually rendered it once they'd pieced the story together. A dim, distant galaxy hanging in the dark, and somewhere near its outer edge, a sudden eruption of light, two impossibly narrow beams of energy stabbing outward in opposite directions, moving at nearly the speed of light, visible in that instant across billions of light years of empty space. That's the image space agencies eventually released, once the picture became clear enough to render. What it doesn't show is the part that actually terrified the researchers studying it. That eruption didn't fire once and go dark, the way every one of its kind is supposed to. It kept firing, in pulse after pulse, for the better part of a day and a half. The story starts with a Chinese satellite called the Einstein probe, whose entire job is scanning the sky for sudden flares of X-ray light. In the early hours of July the 2nd, it picked up a soft X-ray signal from a patch of sky in the constellation Aquila. On its own, that's not headline material. Space is full of things that flicker in X-rays. But roughly 10 hours later, NASA's Fermi Gamma Ray Space Telescope, a completely separate instrument built to detect one of the most violent phenomena in the universe, triggered on the exact same patch of sky, this time picking up a flood of gamma rays, the highest energy form of light there is. To understand why that 10-hour gap matters, you need to know what a gamma ray burst actually is. When a massive star runs out of fuel at the end of its life, its core can collapse in on itself and form a black hole in a matter of seconds. Picture the star's entire core caving inward, faster than the outer layers can react, folding into a single point of infinite density. As that happens, some of the star's own material gets funneled into two narrow jets that blast outward through the collapsing star's own body at nearly the speed of light, punching a hole clean through it and out into space before the star even finishes tearing itself apart. For an observer lucky enough, or unlucky enough, to be looking straight down the barrel of one of those jets, the result is a gamma ray burst, a flash of light so intense it can outshine an entire galaxy for a few brief seconds. Almost always a few seconds. Sometimes, in rare cases, astronomers call ultra-long, a burst can stretch out to several minutes. The previous record holder for the longest gamma ray burst ever measured lasted a little over 2.5 hours. GRB 250702b lasted 7 hours, not 7 minutes. 7 hours in a series of repeating flares, each one lasting around a minute and a half, separated by irregular gaps ranging from roughly an hour to as long as a full day. When astronomers added up the entire span of activity, from the first faint X-ray whisper to the last gamma-ray flare, the event stretched across nearly a day and a half. Nothing in the established playbook for how a star dies produces a burst that behaves like that. It didn't fire once and fade. It kept firing, again and again, like something was still alive out there and still fighting. That alone would have been enough to make this the strangest gamma-ray burst on record. But the timing made it stranger still. In every gamma-ray burst ever confirmed before this one, the gamma-rays either come first or arrive alongside the lower energy X-rays. Here, the X-rays showed up first, and gamma-rays didn't follow for nearly 10 hours. No existing model for a collapsing star predicts that kind of delay. Whatever was happening out there, it was building for the better part of a day before it produced the kind of extreme high-energy flash that Fermi is designed to catch. This is where James Webb Space Telescope enters the story, and its job wasn't to detect the burst itself. Ground and space-based X-ray and gamma-ray instruments had already done that. Webb's job, months later, was to figure out exactly how far away this thing happened, and in doing so, to reveal just how much energy it actually released. On October 5th, 2025, Webb captured the clearest image astronomers had yet obtained of the burst's host galaxy, an object so distant that the light reaching Webb's mirrors that day had been traveling for roughly 8 billion years. Once researchers combined that distance measurement with the brightness of the burst, as observed from Earth, they arrived at a staggering conclusion. Accounting for how far away it was, GRB 250702b was, by total energy released, the most energetic cosmic explosion ever recorded by human instruments. Not merely the longest, the most powerful, full stop. Here's where the story gets genuinely unsettling for the scientists working on it, because a burst that energetic, coming from the death of a massive star, should leave behind unmistakable evidence. Every long gamma-ray burst confirmed so far has eventually revealed a supernova, the bright stellar explosion that accompanies a star's core collapsing into a black hole. It's practically a signature, the smoking gun, that tells you what kind of star died and how. So Webb's science teams went looking for it. Using the telescope's near-infrared camera, they combed through the burst's host galaxy for weeks, then months, searching for the characteristic glow of a fading supernova against the background starlight. They didn't find one, not definitively. The host galaxy itself turned out to be an enormous complication. Unlike most gamma-ray bursts, which tend to occur in small, chaotic, actively star-forming galaxies where massive stars are common and die young, GRB 250702b went off inside a large, unusually dusty galaxy, its explosion site sitting roughly 1,900 light-years from the galaxy's center, out near the edge of its disk. Webb's images show that disk threaded with thick, dark lanes of dust, dense. Enough that researchers openly admit any supernova that did occur might simply be hidden behind it, its light smothered before it ever reached Webb's detectors. One astronomer leading the follow-up imaging described the galaxy's structure as so complex that it isn't even clear whether there's anything left to see of the original explosion at all, and if there is, it's extremely faint. So astronomers were left with an explosion that behaved unlike any confirmed collapsing star, in a location unlike where collapsing stars usually die, that may or may not have produced the supernova that would normally confirm the whole picture. That combination is what pushed researchers to start seriously considering explanations far stranger than an ordinary massive star running out of fuel. The leading alternative explanation is almost as dramatic as the event itself. A team of astrophysicists proposed what they call a helium merger model, and it goes like this. Picture two objects locked in a binary system, orbiting each other for millions of years, the way roughly half of all massive stars in the galaxy do. One of them is a black hole. The other is a helium star, a star that has already burned through its hydrogen and shed its outer layers, leaving behind a smaller, denser core. Over enormous stretches of time, the black hole's orbit can slowly tighten, spiraling closer and closer to its companion, until eventually it doesn't just orbit the star anymore, it falls directly inside it. Picture that moment for a second, because it's almost impossible to visualize using anything from ordinary experience. A black hole plunging bodily into the interior of a star that's still, in a sense, alive, tearing through its outer layers and beginning to consume it from the inside out while the star's own material funnels down into the black hole's gravity well, sparking narrow jets of matter blasting outward at close to the speed of light. This time, not from a star collapsing on its own, but from something being devoured piece by piece from within. Researchers who modeled this scenario argue it naturally explains features that a standard collapsing star cannot. The extreme duration, the repeated flares as the black hole tears through successive layers of stellar material, and even the possibility that a fully formed supernova might never occur at all, because the star isn't purely collapsing under its own weight. It's being actively consumed by something already fully formed and already ravenous. A separate team proposed a closely related but distinct scenario involving a white dwarf, the dense burned-out core left behind by a smaller star, locked in orbit with a black hole instead of a helium star. In that version of events, the black hole doesn't swallow the white dwarf cleanly in one motion. It disrupts it repeatedly, tearing off successive layers of material during each close pass as its orbit slowly precesses, wobbling and shifting with each loop, stripping the doomed object down piece by piece across the very same irregular, hours to days timescale astronomers actually observed. Under this model, every one of those repeating flares isn't a separate explosion. It's another bite taken out of the same slowly dying object. There's a third possibility that researchers have not been able to rule out, and it comes from a completely different family of cosmic violence altogether. A relativistic tidal disruption event, the technical term for what happens when a star wanders too close to a black hole and gets ripped apart by its gravity, its shredded material spiraling inward, and occasionally launching jets of its own. Some of the extreme irregular properties of GRB 250702b, the repeated flaring, the unusual delay between X-rays and gamma rays, bear at least a partial resemblance to relativistic tidal disruption events observed in other galaxies. But researchers studying the burst in detail have been explicit that it doesn't cleanly match that category either. Its gamma ray properties, hard spectrum, rapid variability, and total energy output line up more closely with what you'd expect from an ultra-relativistic jet powered by a compact, rapidly spinning central engine, the kind of engine associated with a genuine gamma-ray burst rather than a slower, more grinding tidal disruption. What makes this event so difficult to classify isn't a shortage of data, it's the opposite. An entire fleet of instruments watch this thing unfold from multiple angles at once. NASA's Swift Observatory and NuSTAR tracked X-ray flares continuing for up to 2 full days after the initial detection. The Chandra X-ray Observatory added its own high-resolution look. Ground-based telescopes, including the Gemini Observatory in Chile, captured deep images of the host galaxy trying to pin down exactly where, within that dusty disk, the explosion actually originated. And Webb, the most sensitive infrared eye ever built, spent hours staring at the same patch of sky, producing an image so detailed that researchers could finally separate the glow of individual stars within the host galaxy from the residual light of whatever happened there in July. Every one of those instruments returned ARIA, usable data, and every one of those data sets, laid side by side, describes an event that doesn't fit comfortably into any box astronomers had built before July 2nd, 2025. It's worth stepping back here to understand why an event like this matters beyond its own strangeness. Every confirmed gamma ray burst up to this point has fit into one of two families. The short bursts, produced when two ultra-dense objects like neutron stars collide and merge, and the long bursts, produced when a single massive star's core collapses. Those two categories, refined over more than 2 decades of observation, have become one of the more reliable frameworks in modern astrophysics, confirmed repeatedly by matching bursts to visible supernovae, or, in the case of mergers, to ripples in space-time itself detected by gravitational wave observatories. GRB 250702b doesn't fit cleanly into either bucket, and that's precisely why it matters. If the helium merger explanation holds up under further study, it would confirm for the first time through direct electromagnetic observation a pathway theorists have described mathematically for years, but never actually caught in the act. Two objects locked together. For millions of years, one of them slowly consuming the other from within, right up until the moment it finally breaks the star apart from the inside. That's not a tweak to the existing picture of how the universe destroys its own stars. It's a genuinely new chapter added to it. A postdoctoral researcher at Rutgers University who has spent months studying the event put it about as plainly as a scientist ever put something on the record. This object, she said, shows extreme properties that are difficult to explain. That's not the language of exaggeration. Researchers who spend their careers cataloging violent cosmic events don't reach for words like that unless the data genuinely refuses to sit still inside the models they already trust. It's also worth understanding just how rare an event like this actually is, because rarity is part of what makes it so hard to pin down. Ultra-long gamma-ray bursts, the small subset lasting more than about 1,000 seconds, are already unusual, representing a tiny fraction of the roughly 1 gamma-ray burst per day that instruments like Fermi typically detect across the entire sky. Within that already rare category, nothing on record has ever approached 7 hours of repeated activity stretched across a day and a half, with X-rays arriving a full day, ahead of the gamma rays that eventually followed. Statistically, an event with this specific combination of properties might occur only once every several years, if that across the entire observable portion of the universe those instruments can actually monitor. That scarcity is exactly why researchers are so reluctant to close the book on any single explanation. With only one confirmed example of its kind, there's no second data point to check any theory against, no way to say with confidence which of the competing models actually describes what happened, because nothing else like it exists yet to compare it to. That scarcity also explains why so many different teams, working independently with different instruments, ended up publishing competing papers on the same single event within months of each other. A team led by researchers using the interplanetary network of gamma-ray detectors focused on characterizing the burst's raw high-energy properties, the hard spectrum and rapid internal variability that pointed toward a genuine relativistic jet rather than a more gradual tidal disruption. A separate team built detailed physical models of the helium merger scenario, running simulations of a black hole spiraling into a stripped stellar core to see whether the resulting energy release and repeating flare pattern could actually match what instruments recorded. Yet another group focused entirely on the white dwarf disruption scenario, modeling how a precessing orbit around a black hole could strip material away in successive passes on timescales that lined up with the irregular gaps between flares. Each paper, published independently, agreed on the same underlying fact. Nothing in the existing catalog of confirmed gamma-ray bursts looks anything like this one. The energy release from GRB 250702b is enough to strain, though not definitively break, the standard models used to explain how collapsing massive stars produce gamma-ray bursts. That's a meaningful distinction. It's not that physics has been overturned. It's that this single event sits right at the outer edge of what existing models can comfortably explain, close enough to the boundary that scientists studying it are forced to seriously entertain explanations. A black hole devouring a star from within, a slow, repeated shredding of a white dwarf across a precessing orbit that would have sounded like science fiction attached to any ordinary gamma-ray burst before this one. As of the most recent published analysis, no single explanation has been confirmed. The helium merger model remains one of the leading candidates, in part because it's one of the only frameworks that naturally explains why the star's core didn't simply collapse in a single, brief moment the way collapsing stars normally do, and why the supernova astronomers expected to eventually find has, so far, refused to show itself clearly through the dust. The white dwarf disruption model remains a live alternative, built specifically around the odd repeating rhythm of the flares, and the possibility that this is a genuinely new category of event. Something that doesn't map neatly onto any progenitor system studied before hasn't been ruled out either. Scientists working on the case have said plainly that a definitive answer will likely require another event like this one to compare it against. And events like this one are, by every measure so far, exceptionally rare. So here's where that leaves things right now. Somewhere roughly 8 billion light years away, inside a galaxy so choked with dust that even the most powerful space telescope ever built can't say for certain what's still glowing there, something either fell into a star and began consuming it from the inside, or slowly tore a dead stellar core to pieces across a wobbling, repeating orbit, or did something else entirely that doesn't yet have a name. The light from that event took 8 billion years to reach us, meaning whatever caused it finished happening long before our own sun had even finished forming. Every instrument capable of studying it, X-ray satellites in low Earth orbit, gamma-ray monitors watching the whole sky at once, and the most sensitive infrared telescope ever launched, all pointed at the same patch of space and came away with pieces of the same unfinished puzzle. That's usually where a story like this would end, with a tidy answer and a name for what happened. This one doesn't have that yet, and it's worth being honest about exactly what that means. It doesn't mean scientists are stumped in the way that sounds dramatic on a headline. It means the leading explanations are narrowed to a short list of genuinely exotic scenarios, and confirming which one actually happened will likely take another event like it, observed with the same fleet of instruments, catching the same kind of signature before the dust and distance have a chance to hide it again. Every telescope that watched this one is still operating. Every observatory that caught a piece of it is still scanning the same skies, night after night, waiting for the sky to do this again. What it has instead, for now, is a data set sitting in the archives of NASA, the Chinese, Academy of Sciences, and observatories across 3 continents, describing 7 hours of the most energetic light ever measured arriving from somewhere far across the universe, produced by something that, as of tonight, still doesn't have a confirmed identity. Astronomers are still watching the same patch of sky, waiting to see if anything like it happens again, because right now the only thing anyone can say with total confidence is that whatever GRB 2507-2b actually was, it broke the instrument that was supposed to explain it. And somewhere out there, across billions of light years, the same kind of object may be doing the exact same thing again tonight, quietly, unnoticed, waiting for the next satellite happening to be looking in the right direction at the right moment.